Another dy1, and another yy0, those few letters and numbers determine how a transformer is connected, how its voltages are shifted, and even where it can safely be installed. By the end of this video, you'll be able to read any transformer vector group like an engineer. Let's start with the notation. Every transformer vector group is written using letters and numbers. For example, dyn11. Each character has a specific meaning. Capital letters always describe the high voltage winding. Lowercase letters describe the low voltage winding. The connection type is identified by the letter. D means delta. Y means star. Z means zigzag. If you see the letter N, it means the neutral point is brought out and available for connection. Now look at the example dyn11. D means the high voltage winding is connected in delta. Y means the low voltage winding is connected in star. N means the neutral is available. And the number 11 tells us the phase displacement. We'll learn exactly what that number means next. Now let's understand the clock method. This is the easiest way to read transformer vector groups. Imagine a clock. The high voltage side is always fixed at 12 o'clock. Think of it as the minute hand. It never moves. Now look at the low voltage side. It acts like the hour hand. The hour hand moves. And its position tells us the phase displacement. Every hour on the clock equals 30 electrical degrees. So, 1 o'clock means 30 degrees. 6 o'clock means 180 degrees. 11 o'clock means 330 degrees. Which is also interpreted as the low voltage side leading the high voltage side by 30 degrees. Once you understand the clock, reading vector groups becomes very easy. Now let's look at the first vector group. These transformers have 0-degree phase displacement. That means the high voltage side and the low voltage side are perfectly in phase. Their voltage waveforms rise and fall at exactly the same time. Examples include DD0, YY0, and DZ0. These vector groups are usually selected when no phase shift is required between the primary and secondary sides. The clock position is 0, which means the LV voltage points exactly to 12 o'clock. Now let's move to group 2. Here, the low voltage side is shifted by 180 degrees. In other words, the two voltage waveforms are completely opposite. When one waveform reaches its positive peak, the other reaches its negative peak. Examples are DD6, YY6, and DZ6. On the clock diagram, the LV side points to 6 o'clock. 6 hours multiplied by 30 degrees equals 180 degrees. Now let's examine group 3. This group has a minus 30-degree phase shift. That means the low voltage side lags the high voltage side by 30 degrees. Notice the word lags. It means the LV voltage reaches the same point slightly later than the HV voltage. Examples include DY1, YD1, and YZ1. The clock position is 1 o'clock. 1 hour equals 30 degrees. So the phase shift is 30 degrees. Understanding the difference between lagging and leading is essential when transformers operate in parallel. Two transformers with different vector groups cannot simply be connected together. Doing so may produce very large circulating currents. Now let's look at the fourth vector group. In this group, the low voltage side leads the high voltage side by 30 degrees. The word leads means the LV voltage reaches the same point before the HV voltage. Examples include DY11, YD11, and YZ11. On the clock diagram, the LV side points to 11 o'clock. At first, this may seem confusing. But remember, 11 o'clock is equivalent to minus 30 degrees. Or plus 30 degrees ahead, depending on the reference direction. That is why engineers simply say, the LV side leads the HV side by 30 degrees. This is one of the most common vector groups used in modern power systems. Now let's look at where these vector groups are actually used. A vector group is not chosen randomly. It depends on the application, the grounding method, and whether a neutral conductor is required. For example, DD0 is commonly used in industrial distribution systems. YY0 is often used in distribution networks, where no phase shift is required. DY1 is used in many industrial power systems. And DYN11 is by far the most common vector group for medium voltage distribution transformers, because it provides a neutral point and a 30-degree phase shift. It is ideal for supplying low voltage networks safely and reliably. Finally, here is an important engineering tip. Many engineers can recognize DYN11 immediately. Not because they memorized it, but because they understand why it is used. It provides a neutral point for low voltage loads. It introduces the required 30-degree phase shift. And it has become the preferred choice for distribution transformers around the world. Once you understand the notation, the clock method, and the phase displacement, reading any transformer vector group becomes straightforward.